World Spaceflight News Special Report.
Live from the central coast of California, this is NASA's JPSS-2 and LOFTID, which will demonstrate a new type of heat shield that inflates for atmospheric reentry.
Joe Del Corso, LOFTID's project manager.
So LOFTID, as Sarah mentioned before, is the low Earth orbit flight test of an inflatable decelerator. And that's an orbital entry demonstration, which is what we did. We demonstrated orbital entry of the HIAD technology, that is the hypersonic inflatable aerodynamic decelerator technology. For anyone who still doesn't know what HIAD is, it's a deployable aeroshell that's stowed for launch and during cruise, then deployed in orbit prior to atmospheric entry in order to decelerate payloads at destinations with an atmosphere. So LOFTID was flown as a secondary payload on the Atlas V launch vehicle. After the Centaur, the second stage of the Atlas vehicle, delivered JPSS-2 to Earth orbit, the Centaur stage then fired deorbit motors and began deorbiting the LOFTID vehicle. If you look at the images on number 2, I believe they're referenced, you'll see some of the activities that we were able to see shortly after downloading all the video of the aeroshell inflating. So the Centaur second stage deorbited the LOFTID vehicle, turned the vehicle on, inflated the aeroshell, and then released the LOFTID reentry vehicle. LOFTID entered the Earth's atmosphere at 8 kilometers per second, which is right on point with what we were expecting. And we were able to track the RV, the reentry vehicle, all the way through splash from both ground and aerial aspects. So both John and Greg are going to talk a little bit more about that. While we're still currently in the process of downloading all of the sensor data, converting it to usable information and engineering units, as well as the visual and the IR videos, we can safely say that based on the recovery of the RV, some of our quick look data and the state of the aeroshell and the information that we do have, that the demonstration was a huge success.
John Donano, who is LOFTID's chief engineer.
I couldn't be happier with the way this mission went and with what we're seeing so far. We are all eager to get the data, all of the data, the comprehensive set of data off of the vehicle, and we're in the process of doing that, but that process will take a considerable amount of time. So I'm going to speak to what we have seen so far and what we have learned from it. So we had the data from the Centaur, and that revealed that our trajectory was spot on. We were delivered right on target at the proper entry orientation, the proper speed and flight path angle. We saw the initial external infrared imaging that was referred to in image 1, and it did, the heating on the outside of the airshell looked uniform. It did not reveal high heating concentrations from what we could see in that video, and that suggests good uniform performance. The outside of the aeroshell, when we recovered it, looked absolutely pristine. The aeroshell and the center body, you would not know that they had been through a very intense reentry pulse. It was well protected by the heat shield, and it looks as if the inflatable structure could fly again. The forward side looks nearly pristine as well. It did sustain some damage, but nearly all the damage on the forward surface of the airshell appeared to be caused by a splashdown and time in the ocean, things that it wasn't really designed for. The process of pulling it out of the ocean and setting it onto the fixture, it sustained some mechanical damage that way. But we did not see damage from heating or from flight on the airshell at all. We saw some minor markings on it that suggest some streamlined flows, but nothing that actually would come close to penetrating through the protective layers. The water, it had made the forward layers heavy and applied loads in the opposite direction for the intended design in flight. So this damage wasn't surprising, and we knew that risk going in, that it could sustain much more damage than we actually observed. So we're very happy with the resulting vehicle that we retrieved from the recovery ship. And Greg will speak to some of the processing on that after we recovered it. We did download video data from the uplook camera. That's the money shot for us. The view of the reentry plasma is it was incredible to watch. And item 6 shows how stable we were with the descent and the parachute deployment. So this uplook camera is a camera at the aft end of the vehicle, looking up behind the vehicle through a protective window. And it showed terrific images of the clean separation from the Centaur, and we could observe the Centaur doing its collision avoidance maneuvers as we drifted away from it. And then it gave us these amazing images of the plasma wake behind the vehicle. It first begins as glowing softly orange, and then it becomes much brighter. And you see the wake field converge towards the center, well behind the vehicle. And this convergence stayed remarkably well centered in the camera view, and this reveals qualitatively that the vehicle is very stable. The orange color then transitioned to an intense blue color from the heating, and the plume you'll see includes an axisymmetric pattern, kind of like spokes on a wheel, that coincide with physical features on the aeroshell, and all that looks nominal. And then we also found that, in the video number 6, the descent and parachute deploy, that the moon happened to be framed nicely in the middle of the window. And that stayed there throughout its descent through transonic and subsonic flight, proving that the vehicle is very stable in all regimes. And that was a wonderful thing to demonstrate. It's hard to get that completely demonstrated on the ground, and so this flight proved a lot of people right. So the uplook camera saw the parachute deploy in darkness, but we're working on ways to enhance that and see it a little bit better from the images it captured, and it was picture perfect all the way down to splashdown. So I guess the natural question is, what's next? We've seen, a very successful mission here, but we still have a tremendous amount of data to work through and to process. We extracted the internal data recorder from the vehicle, and we retrieved the ejected data recorder from the ocean. And so we now have to go through the comprehensive data that was recorded on board. And this includes thermocouples, pressure transducers, heat flux gauges, load cells. The inertial measurement unit is a big one that will help us with the reconstruction of the flight. Fiber optic sensing system. This is its first flight, and we're hoping to get a good map of temperatures in different locations. GPS data, we have avionics housekeeping data on board, and obviously we have the video and the infrared cameras that will help us with the onboard imaging, along with some external imaging data from the Spaceflight team that were airborne and tracked the reentry of the vehicle coming in, and so they got the performing the Spaceflight LOFTID imaging mission. We're able to capture that. So we do have the data downloaded from the data recorders, and it's being processed now, but it will take some time to go through it all and make it usable. And we extracted the single board computers from the camera pods. They were physically extracted from the vehicle and have been sent back to Langley, and they are being processed for eventually getting higher definition images from the onboard cameras. And we will be using all this data to assess the reconstructed trajectory. We'll be correlating our CFD, or computational fluid dynamics, entry environments. We will be examining the inflation system performance, the structural performance of the aeroshell itself with the internal pressures and load cells against those applied environments, and of course the thermal response performance, which is one of the major items we want to get from this.
Greg Swanson, LOFTID's instrumentation lead.
A small team of us were out on the Kahana 2 vessel out about 500 miles off the coast of Hawaii, waiting in the recovery zone to be able to recover the article and ejectable data recorder after splashdown. So we got out there about 2 hours before launch and started doing preparations to recover the RV. The goal was to go get the RV first because that was not designed to float, whereas our ejectable data recorder was. So we first positioned ourselves in a good place to recover the re-entry vehicle. Had a lot of excitement on board when we started getting the data packets, and then of course the IR imagery that Trudy pointed to in the beginning. That was, amazing to see the thing come down under parachute and splash down. And once it was splashed down, we actually could see it with the naked eye, the lights on the vehicle, and so we were able to really easily point the recovery vessel, the Kahana 2, towards the re-entry vehicle and head that way. It was less than 5 miles away, so it took us about 40 minutes to get there. As we were getting there, we were getting everything prepped and ready to get in the water. So we put on the big recovery vessel, there was also a small boat, a 7-meter boat that we put into the water using the large boat's crane. And a small group of us, 3 of us from the LOFTID team and 1 crew member from the boat, headed out on that small boat and pulled up to the recovery, or the re-entry vehicle, which I have to say was one of the most amazing things I've ever done in my life. I mean, pulling up to see something that we've worked on for all these years, just floating there high in the water, no water in the basket. It looked pristine, like it hadn't even flown through space. I mean, that was truly amazing. So once we got to it, we pulled up next to it and we were able to hold on to it. Actually, quick video of a camera I was wearing on my head. You can see me actually holding on to the vehicle as Steve Hughes, the Aeroshell lead, is prepping the parachute legs. We had the parachute was designed to, once it hit the water, to release the actual canopy, and so we had the legs left, and that's what we were able to use to lift it onto the recovery ship. So Steve Hughes is putting the shackles on those recovery legs and then getting it ready. And so once we had all of it rigged up, we were able to attach the lifting point to the big ship's crane, and they were able to get it on to the recovery vessel and in the stand that we had created to bring it home on the boat. After that, it was still dark. That whole process took a couple hours. We waited until daylight to go after the ejectable data recorder. That's our little data module that is about the size of a large lemon. It's also painted yellow, so lemon's a good analogy there. But there's no lights or anything besides it's sending us its coordinates, but besides that, we have no way easily to see it without just spotting it in the water, so we wanted to wait till daylight. So once the sun rose, we went after that, and after a few passes, got that on board and headed back to port. That's lifting the RV off the Kahana 2, and we placed it over near University of Hawaii's Marine Center warehouse, where we've been working on it and inspecting it. You can see in that video, the first thing we do is we did some inspection, and then we deflated it. And once we got it all the way deflated, we were able to go in and remove the panels, remove the system batteries and the internal data recorder. And it was great to get all that out. Once that was done, we lifted it and put it on its side. You'll see that in the time lapse as well. And we were able to pull then all the camera single board computers that John talked about and the upload camera footage. And that's when we first got to see that, which was also amazing. After that, we put it nose up and reinflated it, and we did one final inspection, a detailed photo survey of both the forward and aft side of the vehicle. And yesterday we deflated it one final time, and this morning we got it all wrapped up and packaged and shipped and ready to ship back to Langley.
This is the largest blunt body that has ever re-entered the atmosphere. So this, we made this about as large as you possibly could for the constraints that we had as a secondary payload inside the Atlas. But yeah, the next step is to scale up even beyond this, and we'll need to for the Vulcan engine recovery and certainly for missions to Mars. But this 6-meter diameter was a really large step from what had been demonstrated before, and nothing had been demonstrated as a system at this level of energy from orbit.
Squinting my eyes and blurring my eyes and putting my thumb out there, I would say we're right around TRL-7.
For me, I was pleasantly surprised with how nominal the flight was. We had prepared for, dispersions in the trajectory, and everything was right down the middle to the point where we could see the article coming down undershoot from the ship. I was not expecting that. I didn't want to allow myself to expect that.
I expected charring. I expected some, brown spots. I expected the aft side of the vehicle to have some indication of, significant heating. But the vehicle looks just beautiful. It looks pristine. And I really can't say that enough. It was surprising to me how good the vehicle looked. I had a question very similar to this asked of me at a technology day on the Hill many years back from an astronaut asking, do you really think humans should be putting their lives on inflatables? And I didn't know who he was at the time, and I kind of very offhanded, snarky comment that came out of my mouth that shouldn't have was, well, why not? I mean, billions of people put their lives on inflatables every day. I mean, that's what the wheels on your car are. So it's I don't mean that in quite the facetious way that it came across, but the reality is that we use inflatables and inflatable structures for, a number of different applications, and this is just a very specific application.
And they are incredibly resilient and strong materials. One thing I want to clarify is a lot of times we say this is a flexible system, and people might walk away with the wrong impression there. It is flexible in the sense that we can deflate it and fold it up and pack it into a smaller diameter for flight. And then, but when it's deployed and when it's pressurized, it is a very rigid structure. It does not take too much pressure to make it rigid, but this is not, it behaves much more like a rigid heat shield in flight. It's not as flexible as you might think. The other thing is, I see this as akin to, and this is one of the reasons I'm so excited and just incredibly grateful to our team, so many people involved in making this a success. This is akin to a parachute. If you're talking about a soft good that handles, missions that include people. And we've demonstrated that over and over again, and parachutes have become very reliable and safe. And that's where we're headed with this. This is akin to a first successful parachute test in a different regime, an inflatable heat shield, which if you asked me 10 years ago, I'd be like, that's crazy. But here we are, and it works great.
The cost of the LOFTID project, 5-year duration project, was about $93 million. And just to clarify, about a third of that was hardware in the $30 million range. And future versions of HIAD, depending on what the application is. We estimate, because you're getting rid of, the non-recurring engineering costs that are in there that you don't need to pay for again. We estimate in the $2 to $5 million range. So,
yes, we definitely know enough about the Martian atmosphere. At the surface of Mars, the atmosphere is about the equivalent of what we have here at Earth at 100,000 feet. As my PI would say, if Mars had any less of an atmosphere, we would say it didn't have one. John, do you want to say anything more about that?
Sure. Yeah. Thanks, Joe. This test was a very Mars-like trajectory. We targeted the upper atmosphere and a shallow flight path angle at this velocity and this ballistic number to simulate what we have analyzed for Mars. So it has applications for return to Earth, obviously, and we demonstrated that. But this also has direct application to the environments we see in Mars. About the only difference would be the species of the gas itself. The chemistry at Earth is different than of the atmosphere at Earth is different than the chemistry of the atmosphere at Mars. But we did fly a very similar trajectory mechanically